we go bowling.
All right. Here we go. We're going to do a couple problems from the packet. From that, I would be working either if we haven't started our book or work or whatever, or our labs, but you could be working on other things on the test, depending on how you did that. If you just wrote the answers right in the middle, it's a little harder to get to those answers, but at least it gives you an idea and what potential problems I am looking for. So I'm going to start just from the beginning, and we'll do different ones throughout, and we'll see where we're at when we're done. So I'm going to start at number 1, something simple. It says at 40 degrees, hydrogen peroxide will decompose according to the following reaction. Following data were collected for the concentration of H2O2 at various times. A, calculate the average rate of decomposition of H2O2 between 0 and 2.16 times 10 to the 4 seconds. Use this rate to calculate the rate of production of O2. So, what do? Well, rates, gotta remember, we've been talking about this. A rate is a concentration, change in concentration, over change in time. That is always what a rate is. No matter what situation you're in, that is a rate. So in this case, I asked between, or it was asking between 2.16 times 10 to the 4th, from 0 seconds to 2.16 times 10 to the 4th seconds. So what I want for that is 2.16 times 10 to the negative 4th minus 0 seconds. That's the change in time. And then all I need to do is put the polarity on top. So just to make sure that you assign it to the appropriate values. So I 0.5 minus 1.0. Did I write that down wrong? No, okay. Oh, thank you. Sorry about that. Seems weird to have that big a time.
I believe the numbers seem like exactly the same as the first problem.
It is the first problem.
No, for never mind. In the bookwork.
Are you on the first problem?
Or
This is the bookwork.
Bookwork, see you tomorrow.
Yeah, this is a bookwork. Okay, never mind.
How's econ doing?
Good.
So it says use this rate to calculate the rate of production of O2. So whatever value this is, how does that equal to the rate of O2? That's what I want to know. Is it double? It says 2H2O2 equals 2H2O plus O2. This is different from like the packet where you guys had to make them equal. You have to compare them to each other. So whatever this rate is, this should be half of that rate because there's twice as much hydrogen peroxide as oxygen. So the rate should be half. And it should be the opposite sign, which actually this would not be negative, correct? And let's actually be positive because this one's going to be negative because of that. Which makes sense because you are calculating the concentration of being consumed on the left side, and oxygen is producing gas on the right side. So the rate should be a positive rate on the right side. So it's actually negative half of the original number. So whatever number that is, and you can look on the answer. The answer keys are always on this thing. So you can always check the answer keys to see if you're doing it right. It's on the back page, always. Yeah, it should be half of it. So if this was 3, this would be 1.5 then.
So
And it'd be the opposite.
negative.
Again, the answer's on the back. You can check it out. Okay? Answers are always on the back. And then, without even calculating it, well, I don't want you to look as much as if you can help it, but what would be the rate if I didn't give you data? If I asked you the rate at the next set of values, what would be the rate in comparison to that one? Would it be higher, faster, equal, or slower than the previous one? So now it's asking for the next set of time. Would it be faster, slower, or equal to the rate you just calculated? Slower, why, honey? You're right. Let's take a shot.
Well, because, oh, I
Okay, that's okay. You're right, Rory.
Is it halfway?
No, let's say you don't have data. Let's say you don't have any data, and it just asks between 0 and 50 seconds, compare the rate of 0 to 50 seconds to the rate of 50 to 100 seconds in a reaction. I don't even want to try it again.
don't know.
Yeah.
The rate is consistent to the amount of, like, I guess percentage of what you work on. So to say, like, if you're taking off like a third of your however much you have, take the same amount of time whether you have like 100 grams or 10 grams.
So you say equal?
Yeah.
Okay. The only thing that says equal in a kinetics problem is if the temperature is the same is the rate constant. Right?
Okay, it's faster in the beginning
Why?
because there's more of that item, so there's more like collisions and kind of more like
You're at a dance, and there's 100 boys and 100 girls, and everybody's got to match up. You got to do as fast as possible. After a couple seconds, it's going to get harder and harder to find someone else to dance with, right? Because there's less and less opportunity. That's why a reaction slows down. There are less collisions and less abilities for the bonds to occur, so rates will slow down as you continue. And you can do it mathematically. You can see it. It's less. As a reaction goes, the rate always slows down. That's why we take rates at initial reactions, because that is the fastest, so we get the most data, and it's the purest. So you get pure reactions, pure collisions immediately. After a while, it becomes more and more difficult. If you graph your lab, the first lab question, it does this. Production of O2, it slowly tails off. Until you're not making any more because it's leveling out. You're not making as much. So the rate gets less and less and less. So if you did graph it, if you graphed it, time, and this was concentration of O2, let's say, the concentration would do this over time. It would be a really severe rate in the beginning, and then it would become less and less of a slope. The slope would decrease, which means that the rate is slowing down. Okay? So that would be a visual way of showing it. So that's how we do that one. All right, we're going to jump down to number 4. All right, it says, derive the rate law expression and calculate the rate constant for the reaction. A plus B plus 3C gives you products, given the following data for 15 degrees. So basically, I want the rate constant, or the rate law, I mean, and I want the rate constant. So I want K, which that might give it away. Maybe I just said rate constant, and then on the test you're like, I don't know what the heck a rate constant is. Well, that's K. So right now, if you might want to show some work just to make sure you're doing this right, there will be, this is called a differentiated rate law problem, not an integrated. Integrated needs a calculator to determine things with natural logs and things like that. So what are we doing? What's the first goal? What are you finding in general terms? Luke, what are you looking for in general? What are you going to be doing? There's a couple answers you could give me, but.
Trying to determine the order.
Perfect. You're trying to determine the order of every reactant, right? And you're doing that by isolating experiments, correct?
Yeah.
So do it. Compare your experiments to your rates. Yep.
Some things is no order. Kind of not where you polarities change here, not to be never
Molarity will always change, the rate won't. That's how zero order works.
like in the B column, they're all change.
Yeah.
Slow down. Okay. Let me take a look. So what you can do, good question. With B, what I can do is though, is I isolate, you isolate C. So this one, it's not an unfair question at all. If you look at experiments 1 and 2, 0.4 and 0.1 for A and C, and you're changing the B, and because you doubled the B, look at the rate. What happens? It doesn't change. So the minute that is the case, Camille is wording basically, do I have to worry about that one on other ones when I'm figuring out the A and the C? If that ever happens, we haven't had a situation like that. No, because regardless, apparently, no matter what I do with it, it doesn't affect the rate, right? So it doesn't matter that I keep it constant, right? So that one, that you'd have to take an outside look like, wait a minute, what's going on here? You actually had to figure out B first, so, yep. So there, you know one of the three orders now. So it's kind of like you're looking for two more now. Be sure you give me units.
Did you get 0.003? For C? No, it's 98.
You won't do it?
You got another 2 then, I assume? Yeah.
What'd you do? Oh, fuck. What did you get?
Not
I got-
bad.
I got
I got 0.412.
I got .381. No.
No. I don't get that either. I screwed her up.
Did you guys take the other
I got .381.
That's what I
Actually, .382.
got. Back's at .38.
Really good. What's Please.
The answers are on the back.
Oh yeah, I forgot about that.
Oh, I got it. So damn
So eventually you're going to do stuff like this. It's going to be rate law. You need to do two of them though. Rate equals K, and then it's going to be A. You could write them all. I'm going to do it once. Maybe I'll set myself up. If it's a 0, you can erase them. So right away I knew that B was a 0. So I could write it like that, or I can get rid of it altogether. They both are legit to do. So this one, the rate is clearly a second order. I would state that before I just write it in. I'd actually write second order. If it doesn't come out perfect, you've got to be flexible. You are not doing anything but whole numbers, and your option on the test is 0, 1, and 2. If it comes out really bizarre and it's like 2.5, that is not close enough to round, so you might want to recheck. Maybe you picked the wrong experiments. Maybe you kept the wrong things constant, okay? I believe the second one is first. Am I wrong? C? C is first?
C.
Oh my God. That's like a hack joke.
What the heck?
Am I right? Was it like a hack joke?
Then what do? You stick this into the equation. You pick any experiment you'd like. By the way, on your lab, you should probably pick a couple experiments. Don't just, oh, I'm going to pick experiment 1. Like, I probably do them all actually and average it. Or if a few of them are close and you have one really far off, then I would just get rid of that one. Sometimes you have an outlier. Don't use that one. If you have a bunch that are close, somebody came in, they did 6 studies. One of them, possibly 2 were way off, but the other 4 were really close. Okay, average those 4. Your K. K, and you can look this up, but you just plug it in. I usually just use the first experiment, so you put 0.4. You don't need to put the B, 0.1, and then you put the 6.0 times 10 negative third. You get it, and the key part is the units. The unit is this. Actually, I need to look up the time. It says seconds in the rate. So like, regardless of what the answer is, you look in the back, but the unit is that. Liters squared over moles squared times seconds. You could, if you really don't like that, we haven't talked about this a lot, you could write it like that, or like this, and you always just put molarity and then you put one less, but then it's got to be a negative because this is moles over liters is M. So if I flip that, now that's liters over moles. I would just do liters over moles,
That's always what
and
it
then,
is.
yep, and then the exponent is 1 less than the overall order. So this overall order is 2 plus 1 is 3, so I got to put 2's. Okay? The back says 0.38. If you're close to that, I'm sure it's 0.37 something for you. But I'm just going to write what the answer key says in the back. But again, you plug them in. If you're confused, I don't get how to do the rate. Again, I pick an experiment, I plug in the rate, like all the same line. The rate, the concentration rate, concentration C. I need to show that work. You just plug them in. Questions on it though. This is an important one. Like, differentiated rate laws are really important. Jeffrey?
For like a zero order, how does it affect the reaction?
Doesn't.
So it'd be like would it be like a callus or anything, or just?
It literally is, it's a weird phenomenon that the concentration and the amount has no effect on the rate.
Take it out and then just reaction.
Speed-wise, it still matters with the elements and things. But for the speed, it doesn't affect the speed. I guess that's the key thing to say, too. I mean, if you got rid of it, all of a sudden you're missing elements and things. Yep. Okay. Let's go to number 7. Says the decomposition of H2O2 into H2O and O2 is first order. I'd underline that or box that. From the data in problem 1. Oh, data. Determine the rate constant and the half-life. All right. So, let's talk about that and what it means by that. So, that's funny. Okay, so the rate constant is K, right? When it says first order, the minute you start talking about half-lives and things like that, this is what you should think about. First order. That equation is on your yellow sheet. The only difference is I believe it's written like this. Could be wrong, but I believe that's how it's written, which actually makes it easier.
The half-life equation on there is only for first order?
First order, yep.
I think so.
And don't write on there. If I walk by it, like, you can't write on it. Just know first order is the most common reaction. When you double something, it doubles the rate. So that's first order half-life. That's usually the one that you're asked about. If not, we know how to do that. We know how to do half-lives because we do half of the original amount.
Why is K negative?
0 and first orders have a negative slope. So you need to put a negative in there to counteract that negative slope.
So you always want a negative slope, right? Or do you want positive?
We always want a positive rate constant, so that negative helps because the slope is negative, so the negative makes it a positive rate constant.
First order is the slope.
0 and first. Second
Okay,
is
okay.
not because second order is inverse, so it flips the reaction.
I got you.
Luke?
So when you're solving for the rate constant, your answer will always be positive?
Yes.
But you're just putting in negative special?
Yes, so if you did it wrong, you'll know. Like if you forgot to do it, you'd be like, oh, like you always have a positive rate constant. It's a good thing to know. So what I would do is punch this in. Guys, please look at number 1. If you saw this and you're like, oh, I'm going to do what I did before. I have my rate, and I'm going to punch in the rate and the concentrations and get K. Well, that's great, but I don't have that information. This is given only in time and concentrations. I wasn't given a rate.
Write 'em all.
Show me a good loser, and I'll show you a loser. That's what Cam Newton's quote was. Some people are calling you a poor loser. Show me a good loser, and I'll show you a loser. That doesn't make sense. I know what he's saying. Anyway, so you got to do integrated rate law because integrated rate law deals with time, and this has time in it. So this isn't a guess, okay? So now what you do is you plug it in. Let's talk about how we're going to plug this in. I'll do it in the one that's on your yellow sheet. So what I would do is, let me reread what it's saying. So I want the K. So all I got to do is pick at a certain time. What I would do is the distance of it all. So I would do the final concentration as this. Personally, I'd subtract the initial, and I'm doing it the way that it would be on your yellow sheet. The initial concentration is this. I don't know who asked if it was it Kevin or Logan? Logan, about do I have to write an M if there's a bracket?
Okay.
When you're doing most of the math, you usually do parentheses anyway, but Logan's question was, what if I do a bracket? Do I have to write an M? To be honest, it's not bad if you have the M in the bracket. Technically, brackets mean that. Usually, though, brackets are more often used when you have the formula written in there, not a number inside. So like when I write like this, I know I'm looking for concentration. But when all of a sudden I have 6 molar, the brackets kind of leave. So to me, if I write a number, I should have a unit. I'm not going to mark it wrong, but I'm kind of hoping we're at the point in this journey that when I write a number down, if I don't write something after it, I feel a little uncomfortable. If we don't, that's an issue. That's like first year kind of stuff. Like, do I need to put something after a number? It should just be, what do I put after this number? Sorry, yeah. Did I write something wrong?
Why'd you do like 0.25 instead of 0.25?
Right, you could have picked either one. What I'm trying to do is I'm taking it further down. I don't think it would be, I think you should get the same value regardless. I just,
saying like if you're doing like half-life, you know, half of
right, but it said find the K first and then the half-life, so yeah, you could have done,
Don't
yeah.
we already know what the half-life is?
Yeah, you do. You actually do because it's getting cut in half already. So it's kind of like a weird question to put that in there. But I think you could pick either one. But you have to pick the time that correlates with it. That is important. Units. I will be looking. Every number you write better have a unit. Can't be like, oh, yeah, whatever. I don't need to do that. Someone calculate to see if this is right. So yeah, someone asked, well, what, do I have to show the work for the half-life? If it asks to show the work, you should. Trust me, on the test, you're not going to get bailed out on a problem like this, where literally the first thing is half the amount, and then there's the time sitting on the side. That is not going to happen. You will have to determine it. So there's two ways you could have done it. You could plug it into your half-life equation because it's first order, or what you do is you put the original amount here, and then you take half of that original amount. But you only can find that after you know your K. Yeah. Is that what it says in the back? Yep, good. 3.2 times 10 to the negative fifth. What is the unit? It's first order, so that means that the liters and the moles would be one less than the first, so those would be zeros. So you have choices. I like doing that. You can put 1 over S. Heck, I'm not a fan of this. I have seen that. Not a big fan. To me, that just looks a little weird, you know, with kind of what we normally write. That would be my suggestion. Or 1 over S is great. Please look, as I showed you on the front page on the bottom of the test that we did today, there was a minutes one. Tell you now, 90% of the students did seconds inverse instead of minutes inverse. You gotta look at the time, okay? So I just want to show you how you could have done the half-life, like full out. I'm gonna go back to this equation, because I know we have that here, but what you do is you take half of the original amount, just so you understand what you would do in a problem that isn't done for you, basically. You plug in your K. Yes, you have to put the units, half-life, plus natural log of the original amount. So you do half of the original. Now, I know, I get it. The chart already has it. I understand what half of 0.1 is. I'd still write it like this. If you want to punch it in your calculator as 0.5, that's fine. It's not wrong. Believe me. I'm not in an argument to say the difference between this and just writing 0.05. But what it does is it illustrates that you're understanding what you're doing a little bit more instead of just randomly writing a number potentially. Once you stated before, I would never mark it wrong, my gosh. But at the same time, you may not want to punch it in your calculator like that. You might want to be smart about that. I'm a strong believer in minimal calculating button strikes. When I was a student, the reason why, if I didn't get an A or an A minus or whatever, it was because of error after error after error. That's what I always think about when I'm teaching you guys. What could I help eliminate? All right, so you can figure out the half-life is the time right there. It's 2.16 times 10 to the fourth. Okay? If you want to check that you're doing this right, calculate it once, make sure you're getting 2.16 times 10 to the fourth. Like, this is just algebra now. Like, do you understand how to just execute it all, right? Orders of operations, subtracting, dividing, all that good stuff. Okay? Number 8. Using the answer from the previous problem, hey, we did it. Calculate the concentration of H2O2 remaining after 8 hours if the initial concentration was 5.0 molar. Okay, got to talk about this. So that's what's nice about an integrated rate law. Now I can do a bunch of stuff. I can figure out what's happening at any time in a reaction once. And this is an important step. Once I know a rate constant. Okay, so what I want to know is the amount after a certain time. That is always the live amount. That is not the initial. So that will always be on the left side. That is not the bracket with the little circle that's saying initial. That is the final amount. Okay? Then I need to put in my K. I cannot solve for any other hypothetical problems until you know your K. We will talk about time in a second. What did it say? And then what, if the initial is 5 molar now? Is that?
Yeah.
Thoughts? I want to know, sorry, I want to know about it. I lost it. After 8 hours. Can I do that? Miranda, why can't I do that? Right. So, you need to get that into seconds. So I need to multiply that by 60 and then multiply it again by 60, right? Just, you have to. Or you can make the harder decision and try to turn your rate constant into hours, inverse hours, which is not as good of an idea to ever try to touch any kind of constant. It's just not the smart direction. Okay, so if you do this right, I got 28,800 seconds. You need to have that. That would be, it's not dirty. It's something to trip you up, but what it does is it tests to see if you're understanding units. That's truly what it is. Okay. So then you just calculate it all out. You should do this whole side then. Let's just review this. Whatever this is, what do I do then? Because I want to make sure that we are really clear, because some of us have struggled with this. We haven't had to deal with this as much. How do I get x? Is that right? I mean, generically? Is that right? Luke, is that a hand or just weird stretch? Okay.
Can we can use that half-life equation that you gave us, right?
Yeah, but this isn't a half-life problem. Isn't this asking after 8 hours?
They could find out how many half-lives are in there.
Like, if you did like 5 molar over 2 to the 28,800 seconds divided by 2.16 times 10 to the 4th.
Go knock yourself out.
Okay, yeah.
It seems like the same amount of work.
Yeah. Okay, I didn't know.
To me, I hear what you're saying. To me, if I'm dealing with times and concentrations, just stay in the integrated rate law. If it's purely about a weird situation about half-lives only, then you can start to deviate. That's the way I'd approach it. Because then you're consistently kind of staying in a framework. But there are different ways to calculate stuff. Definitely. All right.
This does not make sense.
You get the answer with that? Do you get 2 from that?
I got 12.5.
That's what I got. That is what I got.
I don't know.
We got more.
3.2 E negative 5 times 28,000. Oops, is it 800? I rewrote it wrong. That could be the problem. Plus natural log of 0.5. Oh no.
Oh, there's 3s.
And then I take E to that answer. Wait, what? Why did I get what they just got? Oh, wait a minute.
Do you want to play with a -1 first? Yeah, you did.
Dirty.
I messed up.
Wait, is there 4 zeros or on that 28?
There you go. Sorry. Welcome to my world of this is when I was a student.
I don't deserve it. You know what? You know what?
My fault. I spaced out in the last problem here now. I was worrying more about the equations. You need to have a negative on the k for 0 in first order. Totally my fault. You need to have negatives. And it tells you that on the yellow sheet. For 0 in first order, I believe it shows you. Or is it first and second, actually? I shouldn't speak before you know what I'm saying. It shows you for a first and second order. Shows you the rate law, the integrated rate loss for both. So this has to be the negative. So I got like 1.989, which it rounds up to about 2.0. All right, we're going to start. How are we doing on time? We're going to go to 4, and then we'll be done regardless. So I am jumping to number 12. It says the rate law for the following second order. So if I'm on the test, I am boxing that or underlining it. Reaction at 10 degrees can be written as, and there's a reaction. Rate equals, there's a rate law where K, oh my gosh, they're giving me the K? What else can I even ask? Oh, here we go. A, determine the half-life when the concentration equals 0.650. Now, this is second order. So you can't use your yellow sheet for a half-life. Now, if you memorized it, I did give you the second order one, where if you take the equations and you give 100% and then 50% of them in the integrated rate law, you could have the half-life equation. But there's no real reason to memorize that. It's second order. So all I need to do is think about what that means for me, okay? So what I would do is this. Integrated rate law for second order, no negative. This is on the yellow sheet, just this is subtracted from here. So I'm just going to plug in things. This is what I would do personally. Is it half-life? I already forgot what we're doing. Yeah. It's a half-life. So I multiply by half here. And then I even gave you a K, my goodness. 8 seconds. So that's what it would look like. So I would subtract this from the other side. You're going to have to use a little bit of parentheses, and then you divide by 0.8. It's important that you're getting this right. Like, you need to check it. Can you take 1 divided by, and then you got to make sure you're dividing them, half of that minus 1 over 0.65, and then divide the whole thing by 0.8. That's A. B. It says calculate NOBR at time 5.80 times 10 to the negative third seconds if your concentration is 0.650. So still same concentration. So now what we're doing is finding a concentration. So now I'm doing this. then finally it says, if NOBR initial was 1 molar, how long will it take for 50% of NOBR to react? So that is a half-life. Right? So how long is that going to be?
I got point. No, you gotta divide. You gotta divide. Yeah, you do. It would not make sense. You're telling me the time's going on, and you get more of something that you. It wouldn't make sense. You. I got .648. I'll put $1 on this.
Yeah, I get it.
Who wants?
Logan.
Logan. Double.
I actually said it.
Double or nothing.
Logan was $1. The answer is 1.5.
Wait, what'd you get?
It's betting.
.648. Double or nothing, Logan. And this one.
I do.
He's betting. The bet is on.
Double or nothing?
How do you get that?
Dude, you know it's illegal to bet over 2,000.
You need, you need to multiply your value at the ending by -1. So after you get this, you need to multiply this, or you need to put this to the -1 to invert it, or 1 over that number, 1 over answer.
Then you gotta.
You have to invert it. You have to flip it. So either to the negative first or 1 over that. So it's like 0.65 or 0.648. I'm not. My brain's not completely connecting this, but if you plug in this final one, I don't know. Maybe there's a real simple explanation for this, and I'm not seeing it. The last one asks, how long will it take? Is it 1, actually? But if you calculate it out, you get 1.25 seconds.
No.
That's doable. Calculate it out.
That's like today in math class. It should be. It should be 1.92.
But it does. Yeah, I'm wondering. You know what? I'm not going to come to here now. I can tell that already.
I pulled a Mason Crosby.
Okay, just a couple more minutes. 13. Just to build off of this, and we're going to do at least one more problem, number 27. Okay. 13's quick. Got to understand in the test, I could come in and out of certain problems and make it kind of fast, something like this. 13's a good one. Using the information in the previous problem, calculate the initial concentration if it took 4.31 seconds for 75% to react. So if 75% react, what I need to think about that 25% remains. Okay? So what you need to do still second order. 0.25 of x. Okay? Says it takes 4.31 seconds. Now, things I will tell you now in the AP exam sometimes like set it up. Set it up properly. I mean, I hope you can look at that and be like, okay, that makes sense. Right, 75% of it's reactant, so what I'm saying is that 25% of the initial amount is left. I'm putting in the proper K. I'm saying how much time that took, and I'm putting it in the proper integrated rate law, which is the second order. It's important stuff. How do I do this? Because I got to subtract these from each other, right, and everything? Jeffrey, what do you do? Do you know?
I put both X's on one side.
Okay. Is there any tricks that I have to do with that?
I also put it like under same.
I know, that's what I'm asking. So, what'd you do?
Just change the one on the far left or over X.
Okay. What does that do then? And then you just leave this one?
Yeah, then you can combine them and get the 3 over X.
Okay, because you're manipulating the values, right? So now this is, because you want to get one variable. I will be very blunt. You're not going to do anything that has to deal with manipulation outside of the realm of being able to work with one variable. But I wanted to show you there are different situations. The extent of this problem would be for me to ask you for the setup. Okay, but that is what we have to do is you have to I guess create the factor to be larger so you have the same denominator always. And then you could easily solve for it. And I think it's like something just under 0.9 or something like that. We have time for one more. I just wanted to stop at like, do we understand where to put things? So like I had in my notes right here, yeah, I multiplied both sides by 4, or both things on the top and the bottom, so then I made it, because 0.25 times 4 would be 1 on the bottom, so that's why you have 4 on the top, if you're confused by that. Last one I want to do for today. 27. We need to do one of these. We haven't even done one technically in class yet. But I have a lot of trust and faith that you are being able to do it because not one person has asked me how to do one yet. And Rory's on question 1 on his bookwork, so I'm confident. The activation energy for the hypothetical reaction 2A plus B gives you C is 8.9 times 10 to the 4th joules per mole. If the original rate of the reaction is tripled at a temperature of 325 Kelvin, at what temperature will the reaction begin? Again, to me right now, it's more about the setup. On the test, I will only ask for 2 things. I will ask for a K, or I will ask for an activation energy. That's all. Was there one on the test that I handed out today? That's weird. Yeah.
Activation, is that E?
You'll be given the equation on Friday?
Is there gonna be all these other tests?
It could be. You'll be given the equation though.
Okay.
Okay? So, what I need by this, let me reread that again. It says the activation energy, so this is what we're dealing with. And maybe I'm writing this down wrong. I know this. Whatever K is here, that's the opposite. So I don't know if I gave you one. I'm curious actually what I gave you. Anybody have something really, is it handy? If it's not handy, don't look it up. Anybody have the equation that I gave it to you in your notes?
I think it's T2.
I don't want to think. Miranda's looking it up. She got it. It was a pre-made note sheet, I thought. Was it? Or maybe not.
$1.
Yeah, it's that.
It's this? And if it's not this, then it's K1 and K2, and then these temperatures just switch. They're both, I think that the other way is in your packet. All right, so let me just reread it again. Setup and knowing where things go is the most important part of this right now. So the activation energy, blah, blah, if the original rate of the reaction is tripled, if the original rate of the reaction is tripled. So the original one I'm going to say is 1, and then I'm going to say it's 3. Don't make it weird. Like, well, I'm going to call the first one 5.7 times 10 to the -5th. So take that. Like, I'm not going to do that. I'm going to do this. It says that the activation energy is this. you need to be able to understand how to do the rest of it. So, it says that the original rate reactions tripled at a temperature of 325. So, this one's 325. Or did I do, wait, or did I flip that wrong?
I think it's the other one.
Is it two? It doesn't feel right that the T1's first.
I thought it was the other way around.
Oh, actually, no. I think you. I'm gonna check it.
I know on the packet.
Are we gonna be given the R too? Or do we have to remember?
No, the R is on your yellow sheet.
Oh.
Something's not feeling right. No, that's right.
Would the 325 go with the T1?
It says the reaction is tripled. Oh, whoa. The reaction is tripled at 325. So I don't remember hearing you say it went to T2.
No, I just said that. I had it 3. You can even you can even see my erasing markers because I had it right here.
Then the R is really important. There's a couple R's on your yellow sheet. Whenever you're given an energy, you need to understand that it's this one. It is on your yellow sheet, but you need to recognize that. Okay? It's really important that you're understanding which ones you're using, and that goes all the time. The other thing that could be thrown, and again, you will not have an X where I have it. You'll be either solving for activation energy or one of these. So if you ever have one in here, you just have to take the e to the whatever is on the other side. And then you have the fraction, and then you just solve out. But a lot of times activation energy is given in kilojoules. You have to convert this to to joules because your R value is going to be in joules. Got to match it up. Okay? So we will talk more about the test tomorrow. We'll try to quickly do an integrated rate law. Please, if you're done with everything else, you have nothing else to work on, you should be doing something with chemistry. If you're like, oh, I'm not going to do anything tonight. You should be maybe working on the old test. Work on some of those problems. I guess I feel like things have been given to you to allow you to be very successful on this at this point. So take a look and work on that. Our test will be on Friday. Okay? Yep.
Feels like awesome.